So I'm just going to talk about both work that I've done and that Steve's done, and the work we've done together as well. So this is a little bit, I don't know, maybe there's some sort of slightly technical bits. I've tried to keep out the equations as much as possible, so hopefully it'll still be useful. So in terms of the outline of this talk, I'm just going to talk a bit about, I'll just give you a quick overview of acoustic modelling. There's a lot of people here doing different approaches. I'll just give what I think is a quick summary. And then I'll talk about BEM, sort of its formulation limitations. They're going to talk about the kind of high frequency hybrid BEM that we've been looking at in particular. I'm going to talk about using oscillatory basis functions, what they achieve. They're going to talk about the challenge then of actually choosing the wave directions behind them. And then I'm going to go on and talk about the work that we're currently trying to develop, which is to do with finding some of these optimal sets of directions numerically, and how this might turn into some sort of iterative algorithm for early time. Draw that together, and I'm just going to very briefly, you see the bottom of the slide behind this iPad, just very briefly just say what the demo is also that I've made in the Sound Lab for you to listen to as well. Okay, so as is well established, we know that generally people use quite different simulation tools at high frequencies and low frequencies. So high frequencies, you tend to assume that sound propagates geometrically. So we've got a wave coming in and hitting an obstacle. Generally, we think that would cause some sort of, we think propagate geometrically, and it's going to be some sort of phase beam. So think of a deterministic method, like perhaps phase beam tracing or image source with phase. And you're going to get some sort of sound shadowing, so you get some sort of shadow region here where the instant sound isn't heard, and then you get some kind of reflected waves or scattered sound in BEM lingo, which are going off. And these are basically not going to show any diffraction characteristics, they're just going to be purely geometric windows in which they're visible or not visible. That means its computational cost is independent of frequency, which is a very big benefit. In fact, it scales with reflection order instead, but it's still usually very low and very efficient. We also find that it's fairly accurate at high frequencies for most scenarios. I think hopefully people would agree it's very, very widely used. We've got Jens Holger Rindel here from Odeon, very widely used piece of software that mostly uses a geometric approach. But at low frequencies, it can be inaccurate, and also in some scenarios where diffraction is important, maybe you have a source behind some sort of that's occluded or through another space or something, perhaps those are a little bit challenging in some cases. And really what we need to know is that we're trying to produce an algorithm that's robust. So perhaps what's important for acoustic modelling for these kind of environments is that whatever we do is robust. Do we know it's always going to work if we use this algorithm? We don't have to tune it too much. So then we have the low frequency algorithms, which directly model the wave equation, so more predictably will include all those effects, but the cost usually goes up with frequency. So the first approach is to chop up the actual medium into lots of cells and compute how they interact, so that would include like FEM and FTDD. And what you find then is that the number of degrees of freedom you have, of course, scales with the number of these cells. If you cut in a volume of air up into lots of things that are small with respect to wavelength, that means the number of them goes up with frequency squared in 2D or frequency squared in 3D. However, the cells only talk to their neighbouring cells, so the actual computational cost of this basically kind of goes the same. We've got a couple of guys later on today and tomorrow talking about how to really kind of push this up to high frequencies. I'm sure they'll tell me this is wrong, but there is certainly certainly has been some issues to do with numerical dispersion pollution effects. If you rely on a wave being modelled by every cell talking to the next cell, talking to the next cell, then there's some potential for kind of carry forward error. And also you can see probably just from this graph, they're very different to geometric algorithms. There's no kind of one reflection plus another thing going on. It's basically everything all talking to each other, all intertwined. On the other hand, with BEM works quite differently. In this, we chop up the surface into small things with respect to wavelength. This means that our number of degrees of freedom scales with a degree of, with an order better, so order f in 2D, order f squared in 3D. However, we have the problem that every element essentially talks to every other element in this numerical system. So we find that our computational cost goes with the number of degrees freedom squared. So something like order f to the 4 in 3D, which is pretty much a game stopper really. However, having said that, there's some other benefits. There's no kind of potential for numerical dispersion because you analytically say how a wave goes from point A to point B. And you can also see hopefully you can see there's some parallels immediately with, or I will say what we'll see later, there's some parallels with geometric methods because what you see in the medium is an addition, it's a summation of things coming from all these different elements. So whereas in geometric method you have a sum of those beams becoming the solution, in this we've actually got a sum of waves from individual elements adding together. And what we're going to look at is how we might use a sum of terms that's more like geometric method in a BEM kind of integral framework. Okay, so we'll talk a bit more about how BEM works. As I said, you've got some sort of discretization scheme that represents the some quantities on the surface, usually pressure. Standard approach is chop that up into elements that are small with respect to wavelength, and then use some sort of low-order polynomial scheme to interpolate on there. Maybe assume that they're constant, or they vary with some sort of low-order quadratic kind of behaviour. More generally, though, you can just write this by saying that the pressure on the obstacle is a weighted sum of basis functions. So, and this is it's a bit vaguer in a way, but it also lets us write different things. It has a bit more scope for trying different stuff out if we use this kind of basis function lingo. In terms of the process, we have a scattering integral that says how this stuff on the surface goes out to some point in the medium. So that's kind of where the wave physics come in. This is our first integral. I apologise, there's not many integrals, but there's one here. So in terms of how this works, you'll have an integral over the surface, you can add things up over the surface. You'll have some sort of kernel function, which I've just rather abstractly called k, because it varies a little bit depending on the boundary conditions, but basically that maps sound onto the surface to a point in space, and you add that all up with whatever the pressure from that basis function is and find out what it's contributing to a point in space. So that happens for the scattered sound, and it goes off to away from the obstacle, but also it can come back and affect other parts of the obstacle, so we kind of have this kind of recursion sort of loop effect kind of going on. We have incoming sound from the source exciting all this stuff in the first place, but then we actually need to map this stuff that's re-arriving back onto our discretization scheme, however we represent this on the surface, and I'm just going to rather ambiguously say that we've got some sort of testing scheme or process that does that. I'll come back to that in a little while. And then usually you turn this into a matrix equation, you set it all up and do some linear algebra and solve it. So that's the general process, and our real question is, can we do all of this with waves that are more basis functions which are more like the waves in geometric methods? So a lot of work's already been done. We have a lot of work's been done by Stephen, also Manuel, who's here as well today. In particular, two main groups worked on this, using oscillatory basis functions in boundary element method. So the idea here is that rather than using lots of small elements, each with a little bit of polynomial to try and represent something that's oscillating, you try and guess what the oscillation is, and then you basically use another oscillatory function to represent it. And the idea is to try and reduce the number of degrees of freedom for a given frequency, and ideally also reduce or remove the dependency of these number of degrees of freedom on frequency, because that's what's driving the computational cost of this whole thing. So the usual form of, hello, wrong order. Hello, there we are. The usual form of this is something like this. So we've got the same sort of polynomial functions we had previously, these b's. Then we've got some sort of e to the I p, where p will be some sort of phase function that says how the phase varies through space. And the idea is that if you've got something that's both oscillating and got some envelope to it, if you knew what the oscillation was, or could take a very good guess, then what you'd be left with is slowly varying with respect to wavelength, and you can use elements that are quite large with respect to wavelength to deal with this. For that to work, you need to have a good choice of the phase functions, Pn, to match your problem. If not, it's probably going to make it worse. And a common choice is to use plane waves. I'm quite aware of them. You can see the bottom of this part of this slide here. So usually this will amount then to choosing sets of wave directions. So we're going to talk about choosing wave directions that match up with the problem that we're actually simulating. So just to give a quick example of how this can work quite well, I'm going to do a very simple example of scattering by just like some sort of 2D plate. time harmonic problem with a wave number k, and we're going to look at an instant plane wave, which is, so it's got this instant direction di here, this unit vector. If we were to look at what that looked like, here we are, here's our vector, there's the instant wave, and in BEM sense, basically, if you just look at the instant wave, that's the wave without the obstacle, so it just kind of passes straight through. What will we do in terms of this scheme? Well, we're going to just use one basis function over the entire plate for this example. I'm going to choose the phase function to match what the instant wave did. My envelope function is just going to be like a piecewise constant over the plate. It should be uniform on the plate. And I'm going to artificially choose this weight to be 2. So some of you might recognise this term. What I'm effectively doing is the Kirchhoff approximation. But it is essentially using an oscillatory basis function. From this you can then calculate the scattered field, either using a boundary integral equation, which includes all the diffraction that you would require, or using a geometric approximation. If I do it first just with the geometric wave, hopefully you can see that they've got that same sort of hard geometric shadow boundary here, and then you will get some sort of reflected wave here, so I've got some interference pattern here because it's just a frequency domain simulation. In terms of the scattered field from BEM, we would say that the instant wave is still going all through, and it's cancelling the instant wave out down here with the scattered wave, and then up here it's causing the reflection. If you put the diffraction into that, then we'd see something more like this. So immediately this is quite attractive for auralisation purposes, because in the previous case you could imagine if you moved around in a space you would cross boundaries where reflections kind of switch on and switch off, and you move into a shadow region where things go silent. Already here you're getting things a bit more joined up. If you move between these regions, it won't sound artificial in that way. Okay, one thing I should also mention while I'm talking about this is that these kind of integrals are quite expensive. If you're computing them over a surface with something that's varying with quite a small wavelength, then for a fixed size surface it's going to scale like order frequency squared. One important thing we've done is one of the developments is that we've produced an algorithm that breaks this down into an integral around the edge of the panel instead. So it's a line integral and a geometric term, so it's a geometric term and the correction. And the correction is order after compute, and there's also some future work which makes it look like it might possibly go down to frequency independent. Okay, so let's get to move on to choosing these wave directions. And there's two real kind of schools of thought on this. One is sort of partition unity BEM, and the other is hybrid numerical asymptotic BEM. So in partition unity, what you do is first of all you divide them into a coarse mesh, sort of large with respect to wavelength on this obstacle. Just zoom in on one of these sides. Then we're looking at one of these elements, and our statement with our oscillatory basis functions is our envelope functions. So we probably use those same sort of polynomials, Lagrangian functions we've seen before. And then we've got these plane wave directions here. And knowing nothing about the problem, a good way to start is to basically choose them to be equally spaced in angle. So if you're in 2D, just in angle, in 3D, then uniformly spaced over a sphere. And that is what Emmanuel and his group at Durham did in 2004. And what they showed is that for a given accuracy, you reduce the number of degrees of freedom you have to use quite significantly, from about 8 to 10 per wavelength to like about 2 or 3, which is already a big saving. However, it still scales with frequency like it does for regular BEM. In contrast, we have Steve's work from the University of Reading, where they try and devise wave directions specific to a certain type of problem. So in this case, we've got this obstacle here. What might we do? Well, we could first of all use that Kirchhoff approximation I had in the slide for the screen on these two illuminated sides here. So effectively assume we've got some sort of pressure doubling or something like that. And then what else might we add? Well, we know that for a scatterer like this, that most of the leading or diffraction comes from the corners. So we could kind of zoom in on those, and if we think about what's happening just on one edge, we can say that this secondary diffraction is either coming from this edge on the left, or it's coming from this edge on the right. And in each case we can write what the phase is, because it's just a surface tangential wave. Summing that up over all the edges of the whole thing, then you can write similar expressions for every edge. And in particular, what's important is that you're now approximating these two things, Fn and Gn, and Steve and his group did a lot of work to show that these are non-oscillatory. So you're capturing all the leading order phase stuff in these, and it's really just the magnitude shaping that's in these. So you don't need anything like the same density of mesh. How does this work for higher order? Well, actually it works very well, because if you had a wave coming here and diffracting this corner and going round, along this side it's basically going the same as if it had come from that corner. So you effectively end up with either anti-clockwise or clockwise waves. They have the same phase functions, and it all comes out very nicely. And that means that the number of degrees of freedom scales like log frequency instead of frequency, and the interaction matrix has log squared of frequency elements. So in terms of the computational cost of this thing, with a standard BEM, this is 2D I should add, if you were going from like 100 hertz, like kilohertz, to 10,000 hertz, you'd be looking at 100 times the number of degrees of freedom, then 10,000 times. This you're looking at like 4 times the number of degrees of freedom, then 9 times. So the differences are tiny compared to like the sort of tens of thousands times scaling if you're doing that conventional BEM. There you go. But moving to 3D makes things much more complicated. And this is what we've been really trying to do through our project. So just to actually just take a little step back first and say how might we be able to apply this approach in 3D, just take a little step back to a simpler thing, which is just like that screen I had before, in which case it's just like one side of that polygon. You've either got some waves coming tangentially from one side or the other, but there's only one face, so we don't have a summation anymore. We've got quite a similar situation. And Steve again has been looking at this with some other colleagues from Reading, looking at this, solving a slightly different boundary integral equation to the one we've normally done in acoustics for ridge scatter. This is a single layer potential, this one's called. And in particular, this just has this, I just mentioned this because it has a special feature that it blows up at the edges of these corners, which means that you need some mesh grading here. So you'll see this in a minute on my 3D mesh, that we have to have a bit of grading stuff of conventional elements near the edge, and then in the middle we can have these bigger elements where we use our oscillatory functions and use a small number of degrees of freedom. So this is the thing scaled up, so like a 2D screen but in 3D space. And you can see this grading around the sides. Now importantly, the grading can get narrower as frequency goes up, so actually the number of elements that way stays the same and you're only kind of increasing in the other direction. So in total, the actual cost scales order F, but in this main part of the panel, the number of wave directions, the number of degrees of freedom we're using is fixed. In terms of choosing the wave directions, we've got some instant wave here, then we'll effectively fold them into the panel according to like Keller's law of diffraction. So there's our first one coming off our leading edge, similar thing off the back edge there, and then if we go to these side edges, it's a bit more complicated. It's kind of a bit of a sort of rotation down into the plane, and similar on these edges here. If we're looking at high order reflection, so maybe D1 reflecting off the back, well, that's going to give us something that's the same as D3. Looking at D3 reflecting off the front, we've already got that direction as well. But these two, if we reflect some of these off the back, that gives us something unique. So we get it's got 6 wave directions there. Again, if we went to higher orders again, that's the same as that one, and that one's the same as that one, so we can lose those. So for this problem, I've got 6 wave directions I need to deal with. In terms of what happens, what you're actually approximating, well, this is the total solution that you usually see on these things. If you subtract off this leading order Kirchhoff approximation bit, what you get left with is it's got these kind of patterns on the plate. And hopefully in those things you can see that there's these leading order diffractions actually are what's causing the oscillation in those areas. Here's a BEM result with just piecewise constant elements, so you can just quite clearly see that that's showing the same sort of things as well. So the accuracy of this thing, I'm trying to wind in the frequency. This is the number of wavelengths across the panel, so this is kind of equivalent to frequency here. And this is the sort of Kirchhoff approximation, so this is kind of better than geometry, but it's like a sort of first order wave assumption here. And then starting to move some of these other BEM terms in there as well, these hybrid BEM terms. And we can see that we can get from like really sort of like 50% error up here, right down to sort of like sub 1% by throwing a bit more kind of numerical effort at it. And importantly, we can control that error by basically changing the polynomial number of these elements, which isn't frequency dependent. The main scheme is frequency independent, but we can actually still get the error down across this broad range of frequencies. So just to surmise this section, this is hybrid numerical asymptotic BEM, which Steve's done a lot of work on. I should add that they've done a lot of other cases apart from just the ones I've described. If you're interested in that, please do ask Steve, because he's done a whole lot of other things as well. We didn't have time to fit them in. Importantly, so we choose the wave directions to match leading order directions in a geometric model, and we break the link between frequency and the number of degrees of freedom. So that's really important. However, it requires a detailed understanding of the problem, and you'll find that whatever you're doing is very dependent on source position and obviously the geometry. In contrast, the partition of unity BEM uses the same types of functions, but just sort of chooses them in a more kind of engineering sort of fashion. So you don't need any detailed knowledge of the problem, but while it does give a really significant fixed improvement relative to standard BEM, it doesn't sort of break this link between frequency and degrees of freedom. And the matrix condition can also be problematic. So really the point of this is that if you get the wave directions right, you only need a few of them. If not, then you seem to need a number that scales with frequency, because what you're really doing is using the oscillatory functions a bit like a Fourier series or something to interpolate whatever's going on. So what we've been working on is trying to actually bring these two aspects together. And what we want is an algorithm that can tune these wave directions to these leading order physical effects. So ideally what we do is find this optimum set of wave directions numerically as part of the algorithm, rather than having to effectively choose them manually for a specific geometry, which is what's mostly happening at the minute. As a starting point, we used an algorithm like partition of unity BEM, which has a lot of wave directions, and then started looking into strategies for throwing the majority of them away. So I've kind of called this sort of culling of coefficients in the interaction matrices in that big expensive loop, or of basis functions like wave directions in the approximation scheme I'm using. One issue with all of this is that we get poor matrix conditioning. So we started off by trying to design that out and choose sets of wave directions for good conditioning. One thing we did carry forwards from our work that we've been doing in the hybrid numerical asymptotic stuff is we wrote this as a Galerkin BEM. And what that means is coming back to this idea that when the sound comes around, we need some process of mapping it back onto the discretization functions. We're going to do that using an integral. So our sound coming off, this is the integral I showed before, sort of trying to explain the wave physics of how a basis function radiates out into space. Then over here we're trying to collect that sound again. And we do that by putting that actually inside yet another integral. Yes, integrals for everything. So we've got another second integral with some sort of testing function t. And that has a numerical cost associated with it, but I think it actually brings out some very interesting aspects, which we're going to try and explain now. So going back just briefly to the conditioning thing, just to explain what we're doing, what you can basically show is that if you're going to have this to be well conditioned, you basically want your testing and basis functions to be an orthogonal set. That when you kind of do these type of integrals with them, that they only show some coefficient if they're basically both the same. Which hopefully you can see that this is a bit like that integral with the middle bit missing out. And essentially, if you've got this well conditioned, optimally conditioned in that sense, then the acoustics will probably make it a bit worse, but at least you started from the best place you possibly could. How can we achieve that? Well, an obvious thing to use would actually be Fourier series, because they satisfy this already. So the testing functions would usually be the conjugates of the basing functions, and then you can basically show that they satisfy this kind of relation. This does mean that we need to include functions up to a point where we get to a wave that's more and more oscillatory until it reaches a surface tangential wave number for the frequency we're thinking about. So that means that the number of them will have to use scales like like order f in 2D or f squared in 3D, but that's the same as we've seen for partition of unity and for polynomial of m. So it's not great, but like I say, it's a set of directions. It's like a dictionary of wave directions to pick from. In terms of how you turn those into directions, well, there's something called a wave number spectrum, where whatever is left that isn't tangential wave number, you kind of push out into the medium. So you can turn these kind of oscillatory functions on the boundary into wave directions. So maybe you can see that where this green line represents the basis function goes down, that's blue. If for the wave that it's kind of representing in 3D space, where it goes up, it's red. So these waves on the boundary represent waves in 3D space, and they usually work in sets of pairs, so you can kind of imagine how these would perhaps be related by some sort of reflection coefficient or something. The geometric link to all this is that normally we think of of waves coming in and just things are reflected according to Snell's law, angle of incidence equals angle of reflection. Basically, this testing function actually does that for you. So if you had a plane wave coming in, so it's got this wave number here, and then you're trying to match it onto a testing function. It's one of these oscillatory functions. So you've got this other wave number here with a minus because it's conjugated. If you put them into some sort of testing integral of how do we map that incident wave onto this testing function, two things become clear. One is that this is sampling pressure at a whole load of points, so it's effectively like having a massive microphone array. Secondly, that this is actually like in which case, this is basically like a beam steering function. And secondly, you can also probably see that this is going to basically turn into some sort of Fourier integral. And if this plane goes on forever, then it's a Fourier transform, and the result is a delta function in angle, which is like Snell's law. The only thing that matches what's coming in geometrically is exactly that angle. However, if we make the thing smaller, then we'll get some spreading of that identity, and you'll get something. This is finite and in 2D, something more like a sinc function. And if you were looking for some particular wave number coming in, your geometric reflection will be equivalent to finding exactly this wave number here, but actually we've got this whole load of side lobes and things going on. So it's like a kind of microphone array detection thing. And this applies actually to the interaction matrices as well. If we had two elements and we've got the scattering integral starting this bottom element and we're moving on to another element where we're running our testing integral, then the bottom one is effectively working like a loudspeaker array and the top one's working like a microphone array. And if our basis function on our bottom array is pointing up, it's going to push energy in that direction. The main kind of geometric lobe of it's going to go that way. And if the microphone array is also looking in that direction, we can sort of put its directivity pattern in there, then it would pick up a lot of that array, and that equates to a large coefficient in the interaction matrix that we're getting. If on the other hand the radiation is going the other way, then you're going to get a small coefficient. If we're going at sort of different angles, because we've got some oscillatory component in this, with beams steering off in different directions. Again, if the directions don't match, then we get a small coefficient. If the directions do match, but the overlap's not great, then we'll get a medium kind of coefficient. But if we were looking at the next element along, then that is right in that kind of main geometric beam. So we see that the elements and wave directions that are geometrically lined up with one another actually result in these big coefficients in the matrix. So the next question really is and they become the most significant. So the question really is what happens when you throw the others away? And what happens really, actually, to the accuracy is not a lot. So there's two. I've skipped a couple of slides. There's two different versions of this here. Which one is with a rectangular window, and one is with a Hanning window, which gives a much tighter sensitivity and scattering pattern from these things. You can see two trends here. The rectangular window has quite a low kind of minimum error, which isn't great, but the condition on it is really, really low. The condition of this matrix that we get out is a very, very small number. In comparison, the Hanning window gives much better interpolation properties, and we get very low error, right the way down to having thrown almost the entirety of that matrix away. So it has very little effect on the error, and it has very little effect on the condition number as well. We can throw all those numbers away. We can make this matrix that was previously the big bottleneck in BEM sparse, and have hardly any coefficients in it at all. And if you follow these kind of points here at the top of the frequency, what does it take to get 10% error? Which I admit is quite a big threshold, but is it too big a threshold for auralisation? There's a question for tomorrow. I don't know. Then we would see that if you look at the number of degrees of freedom here versus frequency, so this is a log scale because otherwise I couldn't get them all on one plot, but the number of elements is screaming off to some high number at order f squared. This is a 2D method, but the actual things that we have in our interaction matrix are an order of magnitude lower than that. So we actually only need order f coefficients in our matrix. And that kind of applies to wave directions as well. I'm going to jump slightly because otherwise I won't get through all this. So if we throw away these small entries in the matrix, we can make the matrix sparse without affecting the accuracy of the conditioning. The minimum number of entries grows with frequency at least an order of magnitudes better, so better rather than slower, than standard BEM, which is really interesting. I just skipped a slide to get on to a more interesting bit, but if you're chucking away wave directions, it's a bit less clear cut. But neither of these approaches are very useful unless you can identify which of these are significant in advance. So, just to say how this might work, which is really where we're trying to go now, we're trying to look at sort of iterative solution of a BEM problem. And this is not that new. If you look in time domain BEM, the sort of transient nature of sound propagation and the delays inherent mean that it's inherently kind of sort of marching on a reflection order kind of iterative approach, where a wave comes in, reflects off something, then that reflection reflects off something else, and it kind of marches on in this reflection order process. I've been playing around with doing the same thing in frequency domain BEM, and the general idea, I've skipped a slide. No, is that? Yeah, okay. So, if we started with a space of lots of directions, and then we assume that we're going to throw some of these small matrix coefficients and other things that aren't very significant away. This is like a sort of state matrix that goes, these W's are reflection order, so we're marching on reflection order. If you started with the matrix in the first reflection order, well, maybe that would come in, and if our frequency is fairly high, this might be quite sparse, because only a few oscillatory basis functions map up with the wave directions that are coming from the source. Moving that across, that tells us we only need to calculate certain columns in our matrix. Of those, we've shown that actually quite a lot of coefficients are effectively not important, so we can throw those away, which means that we only end up with certain terms over here. Taking it across to the next iteration, you then have a different set of coefficients on the right hand side, a different set of columns to fill, but again you can kind of mark which those are, and you're not computing the whole matrix, and again you're throwing bits away that are important, and you're getting some other sets. Now you can imagine how if you did this for long enough, eventually we'd end up computing the whole thing. But in terms of acoustics, really we're trying to get a very, very accurate model of these early reflections. It's a low reflection order. And after that, stochastic methods are already known to be very effective. Or as another little idea, why don't we try and actually numerically search? So we've established that there's things like a microphone array. Why can't we actually search around and find these wave directions optimally at every time step? A bit like these guys looking for planes in the First World War. And in that case, we could have something like where we've got this function coming in, and I've kind of like tried to match, these little markers are trying to match what the direction is that these microphone arrays sat on the boundary of this room are finding. And there's kind of the cost functions in terms of the the sort of wave direction. This is effectively wave direction across the bottom, and it's finding these certain peaks that match optimally. And in this case, because it's just from a source, they've been seeded with some geometric thing for the search, and that's pretty much correct already. But higher order stuff, which is I'm working on at the minute, it's a bit more complicated. But you can kind of see straight away that if you take one of these functions that's coming in and then you reflect that back, that again it's going to only excite certain sparse sets of directions of the second order as well. So there's kind of a system here. And what's really important about this, which is different from everything that's done before, is that when you are trying to do your higher order stuff, you're not doing beam tracing as to purely geometric higher orders and then saying let's add the diffraction. You're actually doing it with all the diffraction in there all at once. So, just to conclude, I've shown, hopefully you've seen as well, that the BEM with oscillatory basis function can exhibit oscillatory behaviour at high frequencies. And also, if you choose these wave directions correctly, then only a small frequency independent number is required. You then find the interaction matrix becomes geometrically dominated and sparse at high frequencies, which is really interesting, because that's typically been the major bottleneck in BEM. And I'm working on an iterative algorithm that actually finds these sets of things as you go along, because noticing that it's sparse is all well and good, but you need to predict where the sparsity is. So that's what this really trying to do. So that wraps that. I'm just going to really say really quickly what my Sound Lab demo is. This is looking at a lot of people here have done work coupling FTDD or FEM to geometric methods at high frequencies, sort of stitching these auralizations together. I've done one with BEM. In particular, what's different about it, what's new. So BEM's already quite interesting for doing these sort of stitched auralizations. One of the main challenges, having read some of these papers, is getting a consistent source definition for the geometric method and the FTDD. BEM, of course, that's straightforward. You just literally write what the source definition is, and that's what turns up at your boundary. There's no kind of injecting it into the mesh, it's just there. And I've done the same thing in reverse. That normally what you'd have done is, so the BEM already knows the data on the outside of the room. Normally what you'd have done is simulated a microarray and computed how the pressure from all those walls comes and contributes to that microphone. I developed a new microarray formulation, which is in a paper. I chose not to put the equation in. And effectively, you can make the microarray any shape. And what's interesting about that is it means you can basically blow it out to the shape of the room where you already knew the data. So I've got an integral equation that, rather than just mapping sound at a boundary to a point in space, which is what people have done before, maps it onto any order near-field compensated spherical harmonic channel. So that's what I'm demoing in the room back there. So thank you very much.